So section 1.2 is all about functions, and a lot of this should really feel like review to you from Algebra 2. So a relation is a set of ordered pairs, and it could look like a lot of different things, but basically if you can graph it in the coordinate plane, it's a relation. Now the function is a more specific type of relation. It is a relation for which every x has only one corresponding y value. So every x can only be paired up with one y. If it's paired up with more than one y, it is not a function. The domain is the set of x values for which your function exists, and the range is your set of y values. And this should all be reviewed so far, all from Algebra 2. So they first want us to determine whether or not this is a function. So remember, every x can only have one y. Now we assume the first is the x and the second is the y, the input, the output. And I notice everyone is paired up with just one y. Now you will notice that this y has two x's that are paired with him, but that's okay. So yes, this is a function. When I look at example 2, this x value is a problem because this x value is paired up with two different y values. So then no, this is not a function. When I look at number 3, I should notice right away that x value of 2 is paired up with a 1 and it's paired up with a 4. So this is another example of not being a function. And then when I look at all my x values, everyone is listed only once, indicating it's only paired up with one y value. So this one, yes, it is a function. The vertical line test is a really neat visual interpretation of that same rule, because if I was to draw vertical lines, pretend that's vertical, through the function, or supposed function, every vertical line should only hit once. Those are supposed to be vertical. So this one passes the vertical line test. So yes, this is a function. And same thing here. Draw vertical lines through it anywhere, and then again, yes, this passes the vertical line test. So yes, it is a function. This one would fail horribly several times. It fails the vertical line test. So this is not a function. Number 8, that's one example of a failing vertical line test. So this is not a function. And 9's kind of tricky. It appears something weird happens. This is a discontinuous function, but right here there's a jump. Notice there's an open circle here and here. If I drew this as my vertical line, because there's an open circle here, this is the only ordered pair that goes through that vertical line, and same thing is happening right here. So technically, this passes the vertical line test. So yes, this is a function. It happens to be a discontinuous function, but it is a function. So determining whether or not it is a function based on algebra, there's a couple different ways you could do it. I'm not real good at coming up with a way to explain whether or not this is going to give you more than one function, or more than one value of y for any particular x value. Sometimes if you solve for x, that helps you realize what's going on, so that would mean it would be y minus 4. So whatever number I come up with for x, if I plug it into this recipe, it's only going to come out with one output value. So yes, this is a function. The other idea is you could think of a visual interpretation. This would be a line. Doesn't matter what it looks like, but it's a diagonal line that's going to pass the vertical line test. Now on this one, if you solve for x, it would be 4 minus y squared, which if you think about what that looks like, it's a sideways parabola. It kind of looks like this, actually. And you don't have to know what it looks like, because I could give you a bunch of different examples. For instance, if I put a 0 in for the x, and I tried to solve for y, I would get y squared equals 4. And look what happens algebraically. I'm not just going to get one answer of 2, I'm going to get positive and negative 2. So for that reason alone, the fact that you could have the ordered pair 0, 2, or the ordered pair 0, negative 2, this is not a function. So you can still take a visual approach. You have to somehow justify this to yourself, whether it is or is not a function. When we're finding domains algebraically, I need you to think about what cannot happen to a function, what would make it undefined. So there's two major issues. And the first one is if we start taking an even root, so what I mean by that is like a square root or a fourth root, whoops, or a sixth root of a negative number. Because remember, if you start taking square roots of negatives, you introduce an I, and we are not going to talk about I's for our functions. And the other algebraic issue is if we start having zeros in our denominator. So basically, what you need to look for in your function is, do you have an even root? And sometimes you have both, but do you have a denominator? And could that denominator possibly come out to 0? So when I look at number 12, there are no roots, there are no denominators, so there are no restrictions, which means the domain of this function is all real numbers, or negative infinity to infinity. When I look at number 13, the issue I see is that there is indeed a denominator, and I know that my denominator cannot equal 0. So let's go ahead and figure out what number would make that equal 0. Let's solve. So we have negative x cannot equal negative 4, which means x cannot equal positive 4. This is my domain restriction. Basically, every number in the whole world is fine except for 4. There's an interval way to write that answer, but I am perfectly fine if you guys leave this as your domain. X cannot be 4, indicating it can be everything else in the whole world. Number 14, I'm taking the square root, which is an even root, of t minus 4. Now I know whatever's underneath the radical must be, it could be 0, or it needs to be a positive number. So what's inside the radical must be greater than or equal to 0. Let's go ahead and solve that. So my numbers for t have to be greater than or equal to 4. Now that's the informal notation. The formal notation would be greater than or equal to 4, would start with the number 4, and then go to infinity. This is the domain notation that I prefer for you guys in college algebra, because that's what you need to know for college. Oh my goodness. 15 has a whole bunch of issues. The numerator has a radical, a square root. That's going to have some issues of its own. And then there is also a denominator. So let's first talk about the numerator's issue. What's underneath the radical has to be greater than or equal to 0. Could be 0, but it must be positive. So if I go ahead and solve that, I find out that my x's must be greater than or equal to 3/2. Great. Now for my denominator, what would make my denominator 0? Well, it's a quadratic, so we're probably going to find two answers. If I went ahead and factored my quadratic, I would find that x cannot equal 3 and x cannot equal 2, because either one of those answers would create a denominator coming out to the number 0. So I have to somehow show, if I think about a number line, that my numbers that are acceptable have to be bigger than 3/2, or 1.5, which 3 and 2 are, and my number can't be 3, can't be 2. So, the domain must start at 3/2, which is 1.5, and then it goes all the way to the number 2, but because it can't equal 2, I'm going to put a soft parenthesis on that, and then it can pick up again after 2, all the way to 3, can't equal 3, and then it can go bigger than 3 all at once. But the important thing is it can't hit those endpoints of 2 and 3. That's why we have soft parentheses on everything except for that 3/2. Alright, I'm not going to give you something that challenging on a test, but that is how you would do it. Okay, evaluating functions. This function notation means take function f and plug in or evaluate it at -2. So 2 times -2 minus 3 is, excuse me, -7. The next problem has two different functions. I want you to start with g of 4, and then eventually go to f of 2. So if I find g evaluated at 4, I think I get the number 3. And then f evaluated at 2 gives me the number 21, and 3 minus 21 is -18. The next problem says evaluate g of 3, and then multiply it by 3. And then evaluate f of -3, and then multiply that number by 4. So If I evaluate capital G at 3, which is this guy right here, I get the number negative 3, and I'll multiply him by a 3 in a second. And then for little f, if I evaluate him at negative 3, I get a negative 9. So this is negative 9, whoops, plus negative 36, which is negative 45. These are not challenging, but little mistakes could be costly. Okay, this one's a doozy, so hang on to your horses. Our function is 2 minus x squared, and we're going to find f of 3 plus h. We're going to subtract off f of 3 and divide the whole mess of a thing by h. So I'm going to start doing this piece by piece, and this is going to take a lot of room, so hang with me. Let's start with f of 3 plus h. So f of 3 plus h means I take my function f, and instead of x, I'm going to plug in or evaluate a 3 plus h. So that's this guy right here. Alright, let's go ahead and simplify that. So we have 2 minus, now 3 plus h quantity squared is really a FOIL problem. It's a 3 plus h times another 3 plus h. So that would give me a 9 plus 6h plus h squared. And if I go ahead and distribute the negative and combine like terms, I end up with a negative 7 plus 6h plus h squared. I'm going to hold off doing anything, keep that number right there. We're going to need him in a second. Now we're going to do the green box, which says evaluate f of 3. That one's a lot easier. Oops, hello. 2 minus 3 squared is negative 7, right? 2 minus 9. Okay, hold off on that for a second. Go back to the original problem. It says take f of 3 plus h, which is this blue thing, and then subtract off f of 3, which is this green thing, and then divide the whole thing by an h. Now you should see some amazing canceling happening. First of all, don't forget negative is a positive, so we have negative 7 plus 7, which will cancel out, and I have 6h plus h squared, all divided by h, which means I can distribute this h under both parts of the numerator and cancel out an h in both of the terms. So what you really have is 6 plus h. And that should be how every one of these weird, funky function problems happen. You should have the constants canceling out. You should have a lot of things canceling at the very last step where the denominator divides into all of them. And you should be just left with a polynomial when you're done. This is a prelude to something you're going to do at the beginning of calculus. I know they're not fun, but you do need to know how to do them. And number 20, whew, same thing. So first we're going to calculate L of negative 2 plus h. Then we're going to calculate L of negative 2. We're going to subtract them and divide by h. So let us begin with the blue part, which is L of negative 2 plus h. So our function is kind of a mess. It's negative 2 times, instead of w, remember I gotta put this guy in place of him, and then we'll square it. Again, instead of w, I gotta put this in place of it. Ooh, this is gonna be gross. Okay, I'm gonna keep the negative 2 in front. I'm going to FOIL this out, so negative 2 times negative 2 is 4, negative 2h plus negative 2h is minus 4h, and then plus h squared. I'm going to distribute the 3 into that next parenthesis. Oops, I should say minus. Minus 6 plus 3h, and then a measly little minus 1. And we're not done yet. I need you to distribute the negative 2, combine like terms, and hopefully get something that looks a little better. Distributed the 2. Just rewrite the rest of it for now. Almost done. You can combine this in any order you want. I'm going to kind of go in standard form order because that helps me keep track of things. Negative 8 minus 6 is negative 14, negative 15. Okay. This is the blue function. Hold on to him. We'll come back to him in 1 second. Now let's find L of negative 2. So negative 2, plugging in a negative 2 for my w's. And just watch your parentheses. This part should be easy. So we have negative 2 times what will be a positive 4, minus 6, minus 1. I'm guessing I get negative 15, but let's double check. Yep. And then finally, go back to what they wanted. They wanted blue minus green, all divided by h. So blue minus green would be minus a negative 15 all over h. So the negative becomes a positive. The 15s will cancel. And then when I divide everybody by an h, I end up with negative 2h plus 11, which is what should happen. You should have a ton of canceling on the last step. If you don't, something is not quite right. Okay, I gotta get a book out. So we're on number 30, page 37, number 85. Let's see. And hopefully you have your book with you, because I am going to briefly read over this. Okay, so we've got a physics problem. The distance in feet that an object falls is given by the function s of t. They use s for distance, I don't know why. And then it's 16t squared. Then t is the time in seconds. So the first part says find s of 0, find s of 1, find s of 2, and find s of 3. So basically they just want you to plug in a 0, a 1, a 2, and a 3. So if I plug in a 0, I get 0. No surprise there. If you haven't started the timer yet, you haven't fallen. If you plug in a 1, 16 times 1 squared is 16 times 1, which is 16. If you plug in a 2, 16 times 4 is 64. Sorry, excuse me. And then plugging in a 3, 16 times 9 is 144. So that's the amount of distance that your object has fallen, assuming it hasn't hit the ground yet. Now, part B says, find and simplify s of 2 plus h minus s of 2 all over h. Now, this should be less complicated because our function is a little less gross. I'm going to do this all in one line, but if you want to break it apart into red and green stuff like we did in the last problem, you go right ahead. So let's start with s of 2 plus h. That would be 16 times 2 plus h squared. That's this guy. And then we're going to subtract off s of 2, which would be 16 times 2 squared. And we're going to divide that whole thing by h. Now, much more simple because the function is less elaborate. So, I'm running out of room. So 16 is going to stay in front while I FOIL this out. Good thing you guys can FOIL well. 16 times 4 we decided was a 64, all over h. 64 plus 64h plus 16h squared. When you distribute the 16, there's still a minus 64 off to the side, still all over h. And we should notice a ton of stuff canceling, gone, gone. And if everybody is divided by the h, you get 64 plus 16h. I'm going to hold on to that because I have a feeling you're going to make me use it in the next part of the problem. Evaluate the expression for h of positive and negative 1, positive and negative 0.1, positive and negative 0.01. So basically we're plugging in numbers that get smaller and smaller and smaller. So I'm going to do this on the calculator because I surely don't want to do this in my head. So going to my calculator, I'm going to program it with my new 64 plus 16. Instead of h, we're going to use x. And I'm going to put my calculator's table in ask mode. Well, you know, I lied. I'm going to keep it in auto mode. And I'm not going to quite answer part C. We could easily evaluate it at all those numbers, but I'm going to cheat. I want to go just straight to the table. Make sure it's in auto mode, starting at 0, counting by ones. The question is essentially saying what happens when you plug in smaller and smaller and smaller and smaller numbers. So as the numbers get smaller and smaller and smaller, oh, you know what? Time out. Hockey pucks. I lied. I want to start at 0. I don't want the table to count by really tiny numbers, maybe. Let's do this. I have a feeling I'm just going to have to suck it up and enter numbers. Okay, so the answer is really close to 64 as you're putting tiny numbers in. No surprise. The smaller the number, the closer it is that your answer is going to come out to 64. Because 16 times something really, really tiny is something really, really tiny. What they're trying to get at is if you go back to the original problem, dividing by h, there's no way for me to evaluate that original function at 0 because it would be undefined at 0. There's an asymptote. But in calculus, you talk about something called a limit. So in this case, the limit for this particular problem would be it was approaching 64 as x goes closer and closer and closer to 0. All right. Sorry, that was done a little weird by me. Apologies. This next question is all about function composition or function evaluation, but instead of giving you a function itself as a algebraic function, I've given you a graph. So here's function f, here's function g. They're equally weird. Let's talk about f of 2. So I'm on the f graph right here. When I find the 2, I need to find where the function is. So either go up or down. In this case, I'm going to go up. The function, when evaluated at 2, gives an output of 1. Now do the same thing, except now go to the g function and find 0. So here's 0, so either travel up or down to find the function itself. It's a negative 2. And they would want you to evaluate 1 plus negative 2, so negative 1. This is starting on the inside, find f of 2. So I'm on my f function. We already found it at 2. We found that it was a 1. So this is really 2 times the output of 1. I kind of like these problems. And then 3 times f of 1. So f of 1, be careful. If you travel up, you'll see a hole, which means that there is no evaluation output right there. You need to travel down and see that it has a negative 2. So it's 3 times negative 2 minus, and then g of negative 1. There he is. Negative 2 times negative 2. So let's see, that gives me negative 6 plus 4, which is negative 2. And that is the lesson for 1.2.